Welcome class. This is again Introduction to Material Science Engineering, and this is the second of two lectures in polymer structures. And when we left off with the last lecture, we had just finished up with the degree of polymerization as the fourth defined term regarding molecular weight. That was one of four, with number and weight average molecular weight, polydispersity index, the ratio of weight average molecular weight to number average molecular weight, and then degree of polymerization being two definitions. One, the number of repeat units within a given single chain, or the number average molecular weight divided by the molecular weight per repeat unit. So now we're going to dive into kind of more macroscopic structural characteristics of polymers. We're going to assume that we have any given defined repeat unit. We can define a molecular weight using the techniques that we just went over in calculations. Now what can we do, and what different shapes can we have and arrangements can we have, and what might that mean to properties? So the first big distinction when we step back from the repeat unit level and aside from molecular weight is thermoplastics versus thermosets. So thermoplastics are basically just a spaghetti tangle of long chains. And in fact, the spaghetti tangle is the classic model sort of used to describe a thermoplastic and what gives it its properties. The chains are literally entangled, and their interaction and to a lesser extent maybe some secondary bonding is what gives them all of their condensed matter properties or mechanical properties, etc. So nice thing about thermoplastics, they can be reversibly cooled and reheated, so they can be recycled. So you can, if they are crystalline, you can melt them into a liquid. If they are amorphous, you can soften them, get them above their glass transition temperature, blend them, reprocess them, and away you go, usually with a small reduction in molecular weight for your trouble. And examples are all the vinyl polymers like polyethylene, polystyrene, polypropylene, PVC, etc. Other ones, polycarbonate, most of the nylons, etc. And the next big category are thermosets. And this is where you don't just have single chains entangled giving you your mechanical properties. You actually have covalent bonds between the chains. So you can either have a few covalent bonds kind of going sideways, linking chain to chain, like you would have in a vulcanized rubber, or you can have a complete network, which comes where you synthesize the polymer with monomers that, instead of just reacting in two directions like you see for polyethylene, can react in three or more. So you literally grow a network that is completely covalently bonded. You can have some secondary bond interactions in the case of thermoplastics, which we saw in the case of nylon, where you had that positive charge on the amine group being attracted to the partial negative charge on the carbonyl. Thermosets go it one step further with full-on covalent bonds between chains. So the obvious big negative implication for that is you can't melt them and you can't soften them significantly. So they're very difficult to recycle, if not impossible. So you're stuck basically burning them in a cogen plant. That has big consequences when we're talking about the volume of polymers that we use in everyday society. On the other hand, there are selected applications where the properties of a thermoset are necessary for the given application, so they can do the job that thermoplastics can't in a lot of cases, so use judiciously. And several types of urethanes, not all urethanes, but many types of urethanes are thermosets, and most epoxies are thermosets, just for example. So aside from thermoset thermoplastic, which we can see here on basically on the endpoints, we can get gradations in between. These are examples of sort of macromolecular structure for polymers. So starting over on the left, you can have linear, just straight chains, and then those chains are attracted with secondary bonding. Very, very minimal van der Waals forces in the case of polyethylene, much stronger dipole-dipole bonds for polar molecules. If you have branches off the side of those chains, that limits their approach, and that's shown schematically on the diagram where the two horizontally oriented chains are set a little further apart with those little side branches in between. And again, we had gone over how polyethylene can be linear or branched, and if you think about the opportunities, say, in a polar polymer that might be branched, you can't get those polar groups in close together where they can associate if you have branches in between. You can think of the branches as being an extreme case of steric hindrance, like that big bulky phenol ring in the case of polystyrene. So typically, comparing the two, a linear thermoplastic versus its branched analog, same repeat units, same molecular weight, just with a few side branches instead of just mostly single chain. The branched version will tend to be weaker, more permeable, have a lower glass transition temperature, etc., and have a lower degree of crystallinity. If we go sort of in the direction of more order, more strength, more association between chains, we can drop a few covalent bonds across the main chains, like we discussed with cross-linking. That is a cross-linked polymer. This is used very frequently with elastomers to keep them from creeping. If you are familiar with the action of O-rings, how we need to maintain a certain squeeze under a footprint, creep is definitely not your friend, and so cross-linking will prevent that. It's very valuable. But of course, if those cross-links are full-up covalent bonds, no recycling. You can't repurpose the polymer just by melting or softening. There are new types of elastomers called thermoplastic elastomers, where those cross-links are very, very, very strong secondary bonds that can be disrupted thermally, and they are a halfway point between a fully vulcanized, a full covalent cross-link, and just chain entanglement. And so those serve an important role in the elastomer world. And then over on the extreme of chain-to-chain association is going away from chains and actually having a full 3D network. And again, this is the extreme of network thermosets. A lot of your two-part epoxies, again, and many other thermoset materials. But to get those, as you can see, each one of those little rectangles representing a repeat unit has 3 lines coming from it, not 2. So that is a multifunctional repeat unit. That's what's necessary to get a thermoset. So each of those repeat units has to be able to react with at least 3 other repeat units to get that 3D network. And so once that's set up, it'll have a lot in common with a metal or ceramic crystal in terms of properties and structure, diffusion rate, and other things like that, looking at the scale of that network. So things that are affected by linear, branched, cross-link, network, etc. types of structure. Thermal properties, and thermal is usually captured by thermomechanical. Other than crystalline polymers, fully crystalline polymers, melt temperature is less important than glass transition. And if you think about that, most properties of materials are controlled by what's considered the continuous phase, the volumetrically continuous phase. As we'll see pictures of polymer crystals, there's always little ends and tucks and loops left over when these huge long chains fold in on themselves to form crystals in polymers. So there's always an amorphous component of the polymers that's between all the crystallites. So the amorphous component of polymers is usually continuous even in the most highly crystalline polymers. Continuous phases control properties. In polymers, that continuous phase is amorphous, however small. So when we talk about thermal properties, we're almost always talking about glass transition temperature rather than melt, although both can be important. Mechanical will be your at any temperature mechanical, yield, tensile, fracture toughness, definitely important for a thermoset. You can imagine a branched thermoplastic, depending on its strength, has a lot more opportunity to deform. One would expect that to have a much higher ductility than a thermoset with a high cross-link density. If not 100%, close to 100% has a chance of being fairly brittle. Chemical properties, the stronger the bonds that are already there, the less likely that you are to want to bond to something else. That's effectively the foundation of chemical stability. So the more covalent bonds you have, generally the more chemically stable you are. And then stability, that last one, beyond chemical, would include things like weathering and most specifically ultraviolet and photolysis and photooxidation resistance. Okay, molecular shape. And so these topics are now repeating and overlapping with other topics, but they each have a little bit different role, or in this case twist, pun intended. Covalent bonds, the hybridized orbitals, define a certain bond angle, but in all cases, molecules can literally rotate around their own bond angles. You've got these very, very strong covalent bonds that are in these specific shapes. We saw the hybridized sp3 with methane, I believe, earlier in chapter 2. But that whole molecule can swivel a bit. And this is definitely true for polymers, where the hybridized orbitals that make up the covalent bonds of the carbons or the silicon oxygens in the main chain can rotate quite a bit. And it's that rotation around each bond that allows chains to bend and entangle and gives rise to most of the properties. And this little schematic here just shows a long, probably carbon backbone. And the little cones that are dotted just show the radius of gyration, the volume that each of those bonds would take up as it rotates around itself, and basically like a little set of Tinker Toys. You do not have to break those covalent bonds to get them to rotate. It takes very, very little energy to make them rotate. So that's why you can get entanglement and disentanglement. You can get deformation of polymers without actually ever having to break the main chain, and that's what leads to deformability and yield. And of course, as we go up in temperature, or if we leave more space between the molecules by, say, introducing a little molecule between as a plasticizer, we make it easier to rotate, easier for the chains to detangle and slip past one another. So this is another schematic of chain end-to-end distance there with R. This is a schematic of a single polymer molecule from the textbook. And so you can see the two ends may be fairly close together, but there's probably a couple, 3 orders of magnitude difference between the end-to-end length and the total length. And this is just to reinforce in your mind how much entanglement you can get, and the opportunity for a molecular interaction with that entanglement. You can think of it as molecular friction, basically, that gives us our mechanical properties. Okay, tacticity. The stereoregularity or spatial arrangement of radical units along a chain. So radical units would be something different, another small molecule that hangs off of a polymer main chain as a side group. So with polyvinyl chloride, for instance, we saw that it was the chlorine molecule that took the place of one of the 4 hydrogens in the repeat unit. So depending on how big that radical group is, its position and the regularity of its position on the chain will determine how much that a polymer molecule can fold in on itself and how entangled it can become with other molecules. So the first definition, isotactic, all of the radical groups are on the same side of the chain. So if the R were, say, a chlorine or was the phenyl group with polystyrene, they would be hanging there on the lower side of the molecule. And this is just a 3D version of it, showing the bond angles if this were, say, a vinyl polymer. Syndiotactic, we alternate sides, but it's still very regular. So it goes from being on the bottom left to the top left to the bottom left to the top left as we index across from one repeat unit to the other. So again, lots of regularity, and for instance, this brings those radicals into a little bit closer proximity. So if they had maybe a dipole-dipole potential bigger radicals, that might give a little bit more stability to the molecule. All kinds of potential there for interaction. Atactic means everything's random, soup to nuts. And if that radical is a big molecule, again like the phenyl in polystyrene, this will tend to lead to very amorphous behavior. It'll be really hard to crystallize this because you try to fold the molecule back on itself and there's this big bulky something hanging off the side in a non-regular group where things can't always fit around it, and so you tend to get mostly or totally amorphous structures from those. Okay, isomerism, again, chemists will probably have seen this before, cis-trans. Biochemists, this is definitely big in the biochemistry world. And this is important for rubber polymers, the isoprenes, and this is polyisoprene, which is a natural rubber. There are many, many variations on this that lead to a whole host of synthetic rubbers, including the butadienes and rubbers that are ubiquitous in industry. So if you look at a hydrogen and a methyl group as being radicals, for the cis configuration, they're on the same side as the molecule, or the same side of the molecule as each other. In the trans configuration, they're on opposite sides, top to bottom. So they're not mirror images, and because they're in a different position along the chain, this would have the same kind of implication as the isotactic versus syndiotactic. They'll be able to fit together a little bit differently, and so this will have implications on packing density and crystallization, which of course give rise to different mechanical properties. Okay, last topic, and I'll display them all here at the same time, are copolymers. What if you needed something that had some of the properties of PVC and some of the properties of polyethylene? Well, you can actually synthesize the two so that you have a single chain or a branching chain that have parts of each type. And there's this is the synthetic chemists and the polymer synthesis folks. It's a total field unto itself in creating these. Many of them are much more expensive than a single type of polymer, but they definitely have the potential for giving very, very unique properties that can't be achieved with just a melt blend of either one. I'll give an example before we quit today. So a random, and again this is a little bit like tacticity, a random copolymer is just the two polymers synthesized such that they're in any order and frequency along the main chain. Alternating means there is a particular order, usually AB, AB, basically like a stacking sequence. And the graphic here shows the red dots are like one type of polymer repeat unit and the black dots are another. So like I said, one could be PVC and one polypropylene, or one could be a nylon repeat unit and a urethane, for instance. Block is where you'll have a significant number of each repeat unit, and then graft, you have one down the main chain, side groups on the other. To give an example of how powerful these are, if any of you are familiar with some of the ion exchange membranes, which are fundamental for flow batteries and some of the advanced fuel cells, they go by the name of Nafion. It's a trade name of DuPont's, I believe. And they are effectively a phase-separated sulfone and fluoropolymer copolymer blend. And it's a combination of block and graft, and the polarity difference is so much that that the one type of very polar polymer, it's so polar it's actually a superacid, ends up forming its own phase. The entire molecule kinks around such that that very, very polar group literally forms its own phase and becomes continuous when it's soaked in water. And the remaining groups are Teflon, one of the most non-polar materials that we can get in the polymer world. And it's that combination of polarity and non-polarity and the continuous phase of the polar phase, which can attract quite a bit of water, that gives it its unique properties. And so it's something that could not be done with a blend, and it required a block copolymer. So here's one example. You could look up Nafion. Okay, another one that we touched on earlier when we were talking about cross-linking are thermoplastic elastomers, and this is styrene butadiene block copolymer. So you can see the schematic of it to begin with. You have the styrene A, so that's just your typical polystyrene, so CH2CH with a phenyl ring. And then you have the butadiene in the middle, B, with that double bond that gives it its ability to move in a unique way as a rubber. And again, you can see the dotted line around the blue phase, and that's related to the styrene part, and then the butadiene is the red in between. And so this is similar to what I was trying to explain with the Naphion, that you actually get like attracting like. In this case, it's not necessarily a polarity difference, but there is some migration and enough association between those that it forms a pseudo cross-link that can be thermally disrupted. So you get many of the benefits of a full cross-link in terms of creep resistance, but all of the reprocessing of a thermoplastic. So this is showing again butadiene obviously being much softer than styrene, since butadiene is a rubber. So this is a picture of a polymer crystal, and this would be a something like polyethylene or another vinyl polymer without any bulky side groups or any kind of branches. Polymers crystallize by folding in on themselves, and this is why approach distance is very important, steric hindrance is very important, the ability to have secondary bonds that hold things close together, all of those promote crystallinity. And of course, when you look at the loops and the ends, those loops effectively, even though they're somewhat regular, are not crystalline. They have a much more amorphous nature, and so they won't follow the same kind of temperature behavior that the main crystalline section will, and will tend to soften at a much lower temperature, and will follow the rules for glass transition temperature rather than melt. So this is described as thin platelets with chain folds at the faces, chain folded structure. Polymers are rarely 100% crystalline. I would say never. Probably the highest crystallinity is something on the order of 90, and that's for some extreme polyethylene fiber structures. It is impossible for all regions to become aligned. So this is a more realistic example where the blue circled area that's indicated with the red lettering, crystalline region, that's one of those folded chain. They're called lamellae. And then the squiggly regions around it are just chain entanglement areas, just the spaghetti pile. So quite often one chain will go in, fold back and forth in one of those crystalline lamellae areas, exit it, and then incorporate into another one. So the lamellae crystals may be literally continuously linked by a covalent bond, but that covalently bonded chain that is present in both may travel quite a long way and entangle in the amorphous region en route. So there's certainly plenty of opportunity for those crystalline regions to move relative to one another, because the chains in the amorphous region can move much easier, slide past one another, so you can actually start displacing and rotating those crystalline regions around as you start applying stress in a given direction, especially if you apply a little temperature. And so we'll get into that a little bit more with mechanical properties of polymers and looking at how a crystalline thermoplastic might deform when it's subjected to uniaxial tensile stress. And those will have very specific regions of output on a stress strain plot, which you can measure. Degree of crystallinity is expressed as percent crystallinity, and it is a volume fraction of crystalline regions to non-crystalline, which will correspond to mole fraction typically, not weight. And most physical properties will depend on percent crystallinity, probably second only to molecular weight in a single characteristic, which determines quite a few properties. Generally, heating an amorphous polymer, especially if it's heated very slowly, will cause the crystalline regions to grow, and the percent crystallinity to increase, and this is for the same exact reasons that metals and ceramics crystallize in the first place, and that's lowering total energy. The more closely associated those folded chain molecules are, the lower the energy. Even if it's polyethylene and you're only getting at best van der Waals bonds, chain to chain, sideways, it's still a bond, and a bond is a reduced energy state. So there's always a drive to crystallize, and so if you don't have steric hindrance or something else preventing it, it will happen. If you give it a little bit of heat to overcome activation energy, but if you have something that's physically in the way, inhibiting it, like a bulky side group or a branch, you may not get very far. So heating, we'll put that as a caveat to heat treating causes crystalline regions to grow up to a certain point. Additives. Very few polymers are used neat. This is independent of a deliberate composite. Even pure polymers, quote unquote, aren't ever typically very pure. Polymer additives are deliberately added to improve mechanical properties, mainly processability and durability. For the most part, the ones that are added to improve processability actually detract from mechanical properties in terms of strength. So you have fillers, which would be an exception to what I just said. Those kind of fall under the category of composites, particulate fillers. Those will add strength and sometimes toughness. In some cases are actually added to decrease cost. A lot of inorganic mineral fillers are very, very cheap compared to the polymer binders that go between them and hold them together. So, but on the other hand, if it improves the properties you need and you can save money at the same time, you know, win-win. So you have some very strong stuff and some less strong stuff there. Some of these would be added for other reasons than just strength. Plasticizers go completely the opposite way. These are small molecules that basically provide steric hindrance. They get between polymer chains in both thermosets and thermoplastics. They open up the network and they force volume and distance between chains, and they allow things to move a little bit. In the case of even network polymers, they increase what's called the free volume of the polymer. They allow it to deform just a little, even though it's still a network and it's not going to slip the way a thermoplastic will. It allows it to move a little more and can increase the fracture toughness. In the case of thermoplastics, it can literally allow those chains to slide right past one another and greatly reduce glass transition temperature and tensile strength both. So again, if you have a polymer that's very, very brittle, adding a plasticizer and allowing some amount of chain slippage will give you fracture toughness and sometimes even a bit of ductility. The caveat there is if the plasticizer migrates back out, which they tend to do, they are not thermodynamically necessarily happy. In the polymer matrix, they will tend to bloom to the surface and form their own phase, and then of course the polymer gets brittle. So something important to remember. And a PVC is classic for requiring plasticizers. Most vinyl polymers, especially those used in thin films and plastic bags and sheets, make heavy use of plasticizers. Something to remember, given that most of these are powerful release agents. So if you're using a thermoset as an adhesive, be aware of the ubiquitous nature of plasticizers in all of your surrounding thermoplastics. If you're going to use the polymer outside, you need a stabilizer. You could use a blocker. You could use a dark pigment like carbon black that literally absorbs light, but for the very top surface layer that is going to be exposed before your absorptive filler can absorb the light, you'll need a stabilizer. Antioxidants, various types of UV protectants. Again, under UV stabilizers and antioxidants, these work by a variety of mechanisms, but they either block the light or they react with the very aggressive molecules that are produced as a result of light polymer interaction. We do have a section on material degradation in the book, and we may be able to touch on it some this term, and we'll get into that a little bit more detail in that, but otherwise it is in the Callister text. Lubricants kind of they overlap with plasticizers. They're literally what they say. They allow polymers to be more easily processed, usually up and around glass transition temperature. You can think of it as a plasticizer that has been deliberately allowed to bloom to the surface so that it's available to reduce coefficient of friction with a processing opposing surface like a dye. And then of course colorants, which again overlap with stabilizers in the case of UV. Flame retardants are used in certain selected applications, although I will note that that is becoming a little bit less popular due to the fact that many of these things are quite toxic, and especially when they're released under heat as they would be in a fire. So take that with a grain of salt if you're looking for flame retardants for a given application. Be careful about toxicity and volatility if they're being used around living things. And that is it for polymer structures. Second of 2 lectures. So after this we'll be diving into defects in crystals and looking at the impacts that those might have on material properties of all types. Thanks so much, and see you next time.